I'd like to introduce our two presenters. We have Dr. Tobias Boehme, and his background is in physics and oceanography. And today he's involved in several research projects in the field of holographic detection of algae and is focused on developing new and innovative algae devices, as well as instrument installation and integration for BBE. He's also a frequent speaker on the topic of HAB. Dr. Detlev Lohse, he studied biochemistry at the University of Hanover in Germany and received his PhD from the University of Düsseldorf in 1986. He spent more than 10 years in fundamental research specializing in plant biochemistry. And for the last 22 years, Detlev's focus has been on knowledge transfer regarding photosynthetic processes in algal pigments. So Tobias, if you'd like to get started, the floor is yours. Tobias?
Yes, I'm
oh, okay.
Now, okay. Yeah. Hello, everyone, and thank you for listening and joining this presentation. You are at the beginning of the day. Here is afternoon right now. The sun goes down in the north of Germany, but I hope everyone can follow me. The title has already told from Carrie. We are specialists in algae class differentiation, and I will show you something about that, and in-situ algae class composition in open water. Detlev Lohse and myself are already explained. I've studied physics and oceanography, and that's the reason if you have some question to algae, that's the reason Detlev is here, because he has a lot more knowledge about the algae. Everyone is hearing me fine? Is it okay? Oh, okay. Perfect. The agenda, I want to show you the methods of the BBE instruments. I'm using live algae for calibration on fingerprints. That's a very important thing. Then we have a general overview of the FluoroProbe instrument for depth profiling in the field. We have also a WorkStation for laboratory sampling measurement. I will show you. And then I have some data presentation, depth dependence of Cyanobacteria, and later on you have some questions. What we are speaking about, phytoplankton, microalgae, Cyanobacteria. A lot of you know already that are microscope pictures of different algae, and that is a common method to look what algae are inside. And this pictures nobody can. Now we see here a mixture of different algae. It's from Sarah Marian and Carola Kennedy. It's from California, Clear Lake area, and they sent us a picture where a lot of different algae are in the water body. What we are looking for, we have the photosynthesis of the algae. We have sunlight depicting on the algae, and we have an excitation light that excitate the peripheral antenna. And the photosystem, we know it from school, they want to grow, they make sugar out of that. There's a thermal loss, and we use the 1% of all energy at 858 and 658 nanometer, the fluorescence we use for our instrument. That is the main situation we use. You know, we have a sun spectrum, and you have a lot of different pigments which have an excitation on different wavelengths. And this that we use in our instrument, that the different pigments have different excitations, and all of them have a fluorescence at 680 nanometers. What is the principle of our measurements? We have excitation wavelengths, and the fluorescence response at 700 nanometer is from a colleague during my study. He had made a looks at the fluorescence at 700 nanometer and gets the excitation spectrum of the different algae. In our instrument, we have different LEDs. We have 6 LEDs to detect them. And if you, for example, we excitate at 450 nanometers, we excitate all the cryptophyta, the diatoms, and the green algae, and no excitation and no emission and the cyanobacteria. If we use a red light at 610 nanometer, you see the cyanobacteria have a big peak, and the others have not so much excitation in this area. That is very easy to separate these both algae groups very easily. but we are not interested on 2 of them. So we have some other LEDs to separate the other algae classes. And we have also implemented in the newest devices LED at 370 nanometers. That is for yellow substances, because yellow substances have an excitation in this area and also have a fluorescence at 685 nanometers, where we measure. And that's a very important thing, that yellow substances, CDOM, and organic matter, which has a fluorescence, we measure them and correct them, and also we measure the turbidity and measure turbidity correction of these instruments. The principle of the measurement, we have 4 and 5 LEDs, which light the algae suspensions, each after each other. We have also an extra LED who makes the light brightness of the LED will control that we have all the time the same brightness to get a good data quality, and we measure the fluorescence signal in a detector. It's in 90 degrees. It's for easy situation. It is like this. What the main focus is, we calibrate excitation spectra. So we calibrate the algae with pure algae solutions. And for algae identification, we call them fingerprint. That are the fingerprints of the different algae, where they get exciting the exciting wavelengths. And I have a little animation I programmed myself, and I want to tell you first what are in my presentation you see later on. Where we have, for example, the fingerprints. That is a calibrated fingerprints of the algae with the different excitation in different wavelengths. We have the fit. That is the sum of all fingerprints. That is the sum of all of these dots. Is a fit of all of that. And we have the measurement here on top, and we have the chi-square is a difference between our fit and the measurement. And we try to optimize this chi-square and to optimize to make them to 0, to get them as low as possible, that the fit and the measurement gets very good correlation, and then we can, out of that, we get the concentration of the fingerprints. Yes, I will start with my animation. You have seen already. We start with that are the fingerprints in this of our instrument. You have the yellow substances, the yellow line, the green line, the red are the diatoms, the cryptophyta, and the blue are the cyanobacteria. And if you, for example, start with only green algae, yeah, then we have only green algae, and then to optimize, the contents of the green algae increase, and that is how much the product of the calibrated values with a number, and the chi-square gets lower and lower, and the yellow white line tries to get to purple the purple. And if you go further on, the green algae get bigger, and the content of the green algae get bigger, and of the other gets lower, and chi-square gets lower and lower. And at the end, we have a very good fit. That is only a simulation. The truth is totally different, but it's a simulation how it works. Then, for example, 10 microgram green algae, it's the same situation, but the value, the product of the green algae get higher and higher, and we get also a very good fit of the chi-square, and we have a 10 microgram chlorophyll A in this solution. Now I want to show you main benefit of us is that we have also the yellow substances correction. If we make no yellow substances correction, we try to get a good correlation with this situation. Then you have not a good fit, and there are 14. You have an overestimation. There's only 10 microgram chlorophyll A inside. You have an overestimation of 4 microgram if you have no yellow substances correction, and that is a very important situation. If you make a yellow substances correction, then you see the fingerprint or measurement of the yellow substance get also up, and we have a good fit, and we have the real content which is in 10 microgram green algae and 5 microgram yellow substances. So that is also very important of if you have a fluorescence instrument, that you also have a correction of the yellow substances. We go to another pure algae group. The Cyanobacteria is no algae, it's a bacteria. And now you see on the right-hand side that the fit gets all the time better. Can you turn off the someone? You hear this phone also? I think. Could you? Okay, I try to go further on. It's a background a little bit. Yes, now you see the fingerprint of or the measurement of the fit gets better, and we get a very good situation that only with pure algae, and we get a very good fit with the measurement with 5 microgram cyanobacteria. If you have 10 microgram cyanobacteria, it's the same situation. Yeah, we get the content of the algae cyanobacteria get bigger, and we get a good fit with this instrument. So it's very easily, if you have pure algae groups, that is very fine. But now that it gets more interesting, if you have 5 microgram green algae and 5 microgram cyanobacteria, then you have tried to minimize the chi-square again with the measurement and the fit, and you see the chi-square gets better and better, and you have a content of blue algae and green algae, which make this fit as good as possible. And you see that you have now 5 microgram green algae and 5 microgram cyanobacteria if the fit works perfect in this situation. Now what we have in nature is the last picture of that. We have a mixture of algae, and if you have a different concentration, you have to multiply a product of the calibrated situation with this content, and you get a better and better chi-square, and you have different groups of algae. You have 5 microgram green algae, 5.2 cyano, 6 diatoms, and 4.8 cryptophyta, and the total content of 21 microgram chlorophyll A, and you have also 5.1 microgram yellow substances. That is the principle. It goes very fast in our device. It took and then we have also the fit. This was just a demonstration how it works and how we use our instrument and what we are doing in this in our mathematic situation. Going back to the presentation. Sorry. We can separate 5 different spectral groups. We call them green algae, blue, brown, red, and mixed. The blue algae are the cyanobacteria, the green algae, and so on and so on. And the different pigments of these different algae we use to separate them and to identify these groups in this with our devices. What is also very important, you have to calibrate your instruments with real algae. If you have no real algae, then you have really a problem to get really good values. Some other devices say you have to calibrate your devices yourself and so on. But I think it is we have in our store we have really green algae, brown algae, yellow algae, and we grow them in a poor condition. That is really poor condition, and to use them for calibration. If you have use dyes, for example, what other users are using, you have, for example, rhodamine, you have an excitation at 525, but the emission at 580, and as fluorescein is the same, and they have no emission at 685 as the algae have. So that is the reason we would be happy to find a dye or something else, which is chemical, to calibrate our instrument, but it is not it's not possible to get something like this. And the reason out of that is that you have a very complex system in the cell membranes, For example, here you have chloroplasma, you get different areas where the light get absorbed, and you have also some pigments like erythrin and fucocyanin, which are from the blue-green algae. And though that's the reason, calibration with the real algae is the best option for good data quality. That is, I wanted to tell you about that. We make a calibration with the real algae. That is, for example, a protocol. We are ISO certified, and we use 5 algae here, and we have make a calibration set for every device you send and get out of our office as a good calibration, and we do it very good. And it is a very our guy who's doing that is really a good, correct person to make these calibrations. The principle, now we come to the device, what we are using. The principle of the BBE FluoroProbe is that you have an LED array which excitate the algae, and we have a photomultiplier who measure the fluorescence. And this fluid that is in the water, then we have an LED array, we have a shield that is a protection shield for the device. We have a temperature sensor and a pressure sensor in this device. And to get a feeling of the size, here is one in Lake Westensee, one of a person who is using the FluoroProbe and deploy it, because there's a shield is not out of around that, but you see later also some pictures with the shield, and that you see here the excitation situation. What are the benefits of this instrument? You have an in-situ chlorophyll determination. You have a determination of 5 algae class. I have explained with this demonstration of the fingerprints. You have a yellow substance measurement and correction. You have a turbidity measurement and correction in this instrument. You have a measurement range of 0 to 200 microgram per liter. Continuous real-time measurement, as you can measure with 10 hertz, 10 measurements per 1 second. You have a pressure and a temperature sensor. The temperature sensor is here on the side and the pressure sensor on the bottom. You have an internal rechargeable battery. You have also an Autostart Plug. You can just use this plug, put it on top of that, and can use it in a normal rope to deploy this instrument and get the data out if you connect it with a laptop again. And you have also a new, it's brand new, it's from last week. We have a cable drum with a Bluetooth connection. So you can get with a laptop the Bluetooth connection to this cable drum. So we have and can just deploy the instrument. Here it is with a shield down to the bottom. And we have also a wiper for long-term measurement. If you install it on a buoy or somewhere else, we have also a wiper. That are the standard situation. We have a standard thing with our FluoroProbe. We have also a workstation. Some of our customers say, okay, we want to deploy the FluoroProbe, but sometimes we get samples from other customers or from other areas of the lake. So you can use also a workstation in that. You have a little cuvette inside with a styrene inside that the algae normally settle down, that they get mixed up. You can just fill that up, make the cup over it, and can start a measurement. But attention, you need an extra calibration with a cuvette. If you have a cuvette inside, there's a different light passes and different optical situations. So if you can't buy a workstation afterwards without calibration, that is, if you want to do that, you have to do it like this. Now some data from the FluoroProbe. It is the migration of dinoflagellates in the Lohse, so a trophic lake in Germany. And you see at 9:30 a.m. you have the depth profiling, you have the dinoflagellates, the blue algae, the cryptophyta, and the green algae in this graph. And in the afternoon at 2 p.m. the dinoflagellates goes down. So they have maybe had enough photosynthetic had enough light absorbed and grow, and then they go down to a depth of 2.5 meters. So that's also you have sometimes peaks of the algae in greater depths. So that is a typical situation, and you use this instrument to make depth profiling to get a composition with a depth in this instrument. I was with a limnological guy on a little boat on a lake down in south of Germany. It's a Seepark Lake, and here you see on the winch there's a FluoroProbe with the Autostart Plug. This plug just can put it on a normal cable or on a rope and deploy it and get the data afterwards. Also, IGI Torch I took with me. That is a more surface instrument for measuring. And we had a very good success in this measurement. They had also a little probe, and they measured the temperature and the dissolved oxygen. And you see that the dissolved oxygen is a very thermocline in this area. On the right side, you see the data of the FluoroProbe. You have the temperature. And then you have a gray line is a total chlorophyll, the green algae, diatoms, the platrotrix, the yellow substance, and the blue-green algae in this graph. If we are looking for the toxins, more the platrotrix and the blue-greens that are optical toxic algae, they are not. The toxins are in the algae, but they are indicator if toxins could be in the water. And you see that the high peak of the concentration is in the thermocline. And this guy was very, because all the time he makes for this microscopes, he only takes the surface area, and he only found platrotrix and no blue-green algae. And now he took some samples in this area and in this thermocline. Then it was much more to find for him, and he was very happy to make this measurement. It was last year in October. Application of the FluoroProbe, you have long-term monitoring of algae composition, climate change, invasive species, ecological change of the habitats. Then you have an impact of nutrients and pesticides, and phytoplankton that is also often used for identification of lakes, fight campaigns of special aspect, installation of buoys and platforms. Yeah, you have the buoy. You see the FluoroProbe on the top of this on the bottom of this buoy, and for long-term monitoring, also with a wiper is installed there, and depth range for 100 meters. If they use it on oceanographic vessels, they don't want to deploy twice. That's the reason we have a depth pressure housing for 1,000 meters, but there are no algae at all. It's in above 50 meters where the algae are really important. It's just for operation. Then are the fluorometers. You have a lab analyzers. You have an online analyzer, a flow-through system, the algae online analyzer guard, the FluoroProbe, and the IGI Torch. It's a smaller instrument for lake measurement. Yeah, that is what I want to tell. Thank you to Carrie and Tim for making this presentation happen. Okay, thank you.
Well, thank you, Detlev and Tobias. That's terrific. We do have a question from Lorraine. When we have the mix, we multiply the concentrations by what factor?
Yeah, we have a calibration of the instrument, and this calibration has, if you have green algae, we have a reference in that is, and then we normalize that, and this we multiply this concentration where we know which is inside with this micrograms per liter, and out of that we get the concentration of the different algae classes. But the fit should be very good. Detlev, you want to change something else also? You have to turn on your microphone, please.
Okay. Well, what we have is in our software, you can see a matrix where you see every value which you get from fluorescence for 1 microgram of a certain algae species. And this is the ground value which used to multiply to get the end concentration. So therefore, if you have a view on our, let's say on our website, you can find some more information, or we can send it to you. that you can easily understand how this is made. I think the good way is that we have different algae classes, and we can also add an additional algae classes when we think that it would fit better to the algae which we have here in our mixture. So that means that it can be individually adopted. Then because we use our algae from our laboratory, as shown from presentation of Tobias, which are representatives for the algae classes, but this can also be included individually when you think that you have an algae which is like, let's say, a little bit different in the pigment pattern. So this would improve also your quality of your analysis, but in, let's say, in most time, and on almost most times, all of our appliers use this fingerprint as we propose in our instruments.
And you see here that are normalized for 1 microgram per liter, and that is calibrated in our laboratory, and we multiply this with a content to get the best fit out of that. And that is how we try to get we multiply all of them, getting bigger and low again to get the best fit, and out of that we have the content of the algae.
And of course, what is important, that there is a linear relationship between the fluorescence intensity and the amount of algae which are inside. So that stands for all of our analysis.
So this is me, Lorraine. Hi. So you mean that I should have my lab samples to calibrate my FluoroProbe observations, right? My FluoroProbe measurements, so that I can find that factor and then correct the concentrations I got from the FluoroProbe.
Sorry, there was some mismatch between, so that I could not clearly understand. Of course, everything comes to you calibrated, and you do not have to do anything with the calibrations. If you think this should be improved, then you can, of course, do your own calibration with algae, but we do not recommend it. So we think that our algae, and we can differentiate to up to 5 algae classes, would fit to almost all situations that you will find. But as you know, this is biology, and biology means that we have also, let's say, different situations. For example, nutritions, we have sunlight, and so on and so on. So that means that we have different factors that affect the composition of the pigments. And this means that it is possible to add your own fingerprint for your special purposes. Okay?
Okay, thank you. Sounds good.
Okay, guys, we have another question from Robert. How do you handle clumps of cyanobacteria in the system? If you are using single particles, how does this technique compare with flow cytometry?
Yeah, that's difficult. Clear, that's really difficult. We know about these facts. Well, what we know is if we have clumps or we have high blooms, you see it sometimes at the surface of lakes, then the concentrations are extraordinarily high. So therefore, we would not get, let's say, real numbers from these measurements, but they are mostly so high that they are very often out of range. We have other situations, especially here in Germany, we know about, and perhaps you think of this, of microcystis. Microcystis can also form colonies, and the colonies have a very high density of algae cells, and we cannot really resolute these algae densities so that we get that numbers. What we see is that we have high fluctuations in the results when such a colony passes the light path of the instrument. That is an indication for that. But usually when you are in such a situation, you can normally see by eye that this is an abnormal situation. So therefore, this is a difficulty which we cannot solve. We tried, or I tried myself, for example, to find a solution by ultrasonic. But ultrasonic in the fields, it does not work. So therefore, we have not a clear resolution for that. What we only can say is, despite the advantages with the measurements of fluorometry, you have some difficulties insofar that colonies come or something like this will not give the real numbers of the amount of cyanobacteria inside of the water.
Also, if you use a flow-through cytometer, they have a lot of problems with this colonize. I think
Yeah.
that, that they sometimes, I saw one, I did not operate it, and it blocked all the time because the big colonies go to the flow cytometer. Yeah, that is also a problem for both instruments, I would say, if you have these big colonies. Yeah.
And even camera systems like FlowCam also get clogged, for example, and will not be able to determine the right amount and the type of algae that is going through. So therefore, it's a difficulty which we all have doing this analysis. And even under the microscope, that is the other question what we also have from time to time. If you have such colonies and you want to get the information about the cell density, it's very difficult to find the right numbers because it's so dense and you cannot find the right numbers. Yeah. Other questions from your side?
Does anyone else have any questions for either Detlev or Tobias? All right, Robert has a follow-up question. I guess the critical point is the sensitivity of the system. How many cells do you need to make the conclusion?
What kind of conclusion, I may ask? What is the conclusion? What does it mean?
You can just make a microphone on and ask directly.
Sorry?
We're gonna.
Which kind of conclusion does it mean as a threshold, or does it mean that we have no chance to have this high resolution to determine the real amount?
We have the minimum is 0.01 microgram per liter, but if you have very low content in the water body, then it is very difficult to separate the algae classes. Yeah? As up to 0.1, you have a good separation possible, but the sensitivity at all is 0.01. Yeah, and I don't know. Depends how much cells there are. Depends on the size and how much chlorophyll A they have. But that is what I would say. And
another point is that, of course, imagine you have for example, 100 microgram of green algae and 0.5 microgram chlorophyll of cyanobacteria, then it is very difficult to find an exact number. But if the amounts are rather low, let's say below 5 microgram per liter, it's easy to make this differentiation with the algae, even at that low amount of algae. So therefore, I think it depends always on the total amount of chlorophyll A which you have in your sample. But as we know, it works quite exactly There are other points which have to be considered. That is, for example, if you work in turbid waters where you have reduction of the transmission, so that the light of excitation is not that strong. We have, of course, for this purpose also turbidity compensation, which is also helpful to get the best numbers from your analysis. All right. Liza Klecker. Recalibration can be recalibrated in use. Yes, we need it in Germany because of the algae. Yeah, we have the algae in our lab. If you have algae in your lab and you have a method to do this calibration by yourself with another method for comparison, for example, pigment analysis by HPLC, then you will be able to perform the same calibration as we do here in Germany. But almost all of our customers send their FluoroProbes or other analyzers to BBE to Germany. Unfortunately, no one will be able to provide a lab for calibrations in US America. Maybe we can do this in the future if you buy so much of the FluoroProbes.
And what is the recommended interval, Detlev? Is it every 2 years?
Yes, 2 years is quite good. We have, of course, a certain way to check the functionality of our instrument. For example, for the FluoroProbe, we have a cuvette prepared with a fluorescent material inside that can be checked time by time, for example, to check if the results or the values are still stable. And this can lead that you can continue for more than 2 years. But in general, we recommend to perform these calibrations every 2 years.
And Lisa, that would be arranged through us, PP Systems. So if that's something you wanted to do, over the winter, which is a good time when the instrument's not in use, feel free to contact us and we can make the arrangements for you.
And we try, of course, to send it as soon as back as possible so that you will have this FluoroProbe in your hands before the next season starts, of course.
And so we've got another question from Robert. Is picoplankton a problem that is sort of 1 to 2 micrometers in thickness? And how does the depth measurements compare with surface measurements of organisms?
The first I want to answer, the second you. The first that is a bit of advantage of the FluoroProbe, of all the fluorescence methods, that we also measure picoplankton, which you could not see in the microscope, but if they have a fluorescence, we can measure them. That's the reason sometimes the fluorescence has a bit much bigger value than the microscope, because you can't see them in microscope, but if they have a fluorescence, we will measure them. The second is your question, Detlev.
Okay. Well, I think you can very often see that there are high differences. And this is, of course, a good reason to use a submersible instrument, not only the FluoroProbe, but in general, a submersible instrument. You can see from the example that Tobias showed in his presentation that you will find sometimes in a certain depth high concentrations which you cannot get from measurements from the surface. If you start, for example, if you get satellite observations, and you will be able to penetrate the first 1 to 2 meters, it will not give you the same information. What we have, and this is really a big advantage of all of these instruments, you have a high density of informations. That means that we will have up to 3 measurements per second, that you give information of a complete profile. Measurement from the surface it's only the surface. And we know that algae adapt to different surfaces because they have to balance between, let's say, the bright sunlight with its UV radiation. They have to adapt to the amount of nutrients that they find inside of the water. So therefore, many of the algae have something like a buoyancy, which allows them to go to different depths depending on the situations. So it makes really sense to determine not only at the surface, although it might be helpful, let's say, for bathing waters to get a first understanding what is going on here. But in general, what we see is that is absolute necessary to make profiles. So for example, we are working in a project where we are using the FluoroProbe to check the quality of LiDAR measurements or satellite measurements to obtain the real values which are inside of the water. So it makes really sense to do this. And I'm quite sure from long experience that measurement of profiles is absolutely necessary to get real results.
But we have to say also, if they swim on top of the surface, yeah, that is all the time the problem. Then you have take a sample and use one of our lab analyzers. Because if you, on the surface, if they really swim on that, yeah, then you really have to take samples. And a lot of our customers do that also. They just take the upper 5 millimeters to get these values. That is a problem. Yeah.
Yeah. Great system. Yeah, I agree. Costs for lakes. Well, I think this is a question which can be easily answered by Tim.
Yeah, Robert, we can send you some information, pricing, and so on. So I'll arrange to email that to you following the presentation.
Yes, and we have also IGI Torch. Yeah, I shown at the end that is only for Cyanobacteria and total chlorophyll and turbidity. There's no yellow substance correction. That is a little bit more cheaper than the other thing. You have to decide. But Tim is a good guy. He will support you as good as possible.
I also would like to invite you to have a look on our website where you can see these different instruments. For example, if you are also interested in the other instruments, which are only shortly introduced by Tobias, you can see more information about this, and you can, of course, ask Tim or ourselves directly to get more literature from BBE.
All right. So we've got another question from Lisa. Can you speak to the relationship between the cryptophyte signal and phycoerythrin?
Well, indeed, we measure cryptophytes. We measure the cryptophytes as a total organism. That means we measure the influence of the pigments inside the cryptophytes on the chlorophyll A. Therefore, we get the signal from the chlorophyll A, but the phycoerythrin inside of the cryptophytes, of course, affects the signals of the chlorophyll. The phycoerythrin itself, it's also a fluorescent compound. Well, it's a pigment which has some other features. Because it is excited, let's say around about 550 nanometers, and will send the fluorescence out at around about 570, 590 nanometers, which can of course be measured, but the phycoerythrin itself is not a mass for the amount of algae or the cryptophytes inside of a water sample. So therefore, I think it's much better to perform these measurements for chlorophyll A, although phycoerythrin measurement can show you that there are, let's say, cryptophytes inside of the water. But this can also be red algae or cyanobacteria, which have also sometimes higher amounts of phycoerythrin. So I think the analysis of chlorophyll A is a better solution. recently we started to find out if we can also measure the phycoerythrin itself, which is released, for example, by damaged cells, as we do it for the phycocyanin. And we will be able to do this, but we struggle if this is really important information for anyone who wants to know about the algae content. So therefore, there is a relationship, but the measurement of phycoerythrin does not say so much.
Please, in addition, we have a phycoseria that is for unbound, that measure unbound phycocyanin, and that is for also for cell lysis of cyanobacteria, but it is a different presentation. That is our phycoseria. Please go on our website, and then you see something about that. And that is also to determine waterworks and so on, if the cell lysis starts, and if and then to see that is an indicator that toxin and taste and odor compounds are deployed in the water body.
Okay, so I think we'll take one last question from Robert. The EPA is involved in space monitoring. Does this system relate to that measurement? Sort of another parameter that can be used in connection with satellite monitoring?
We are worked very hard on that right now. In the Clear Lake area, if I can give you some context of this group, we have a lab analyzer there, and they measure a lot of contents in the water body. And they have also a satellite that says something about cyanobacteria, and the relationship is very good. We can all the time see in the satellite should we measure or not, but and then afterwards we see the same situation as in the satellites. In Germany, there's a big ferry box project, and they try to combine the satellite data, and they have to put all the data online to the database, because our NASA tries to get this information as fast as possible to get this ground truth data. So that is also a situation that there is something working together in that. That's we hope that they not get they need all the time ground truth data, and we do our best to give them as best as possible. And there's some institute in Germany that work also on that. In US, I have no information about that. The NASA has already bought 2-3 FluoroProbes on the buoy in the lake, Great Lakes, Tim, I think. And I think they also do something in this with these buoys and the FluoroProbe to check with their satellite data, as far as I know. But we have sometimes not the information what they do with our instruments.
Yeah, so I mean, obviously we've got a number of customers, both the U.S. Geological Survey, NOAA, EPA as well, that utilize the FluoroProbe, the Algae Torch, the FluoroProbe, as well as other BBE devices. So it's likely that they are using that for validation of satellite imagery.
And also the FluoroProbe is also this algae groups, yeah, and that's the reason our instruments are very good, because also the satellites can only measure algae groups. Yeah, they could not separate really special algae, and that's the reason we have not the same wavelengths as the satellites, but we are in the area where the satellites has also its wavelengths, yeah, to look the backscattering, yeah, of the water color. So that is I think that is a good device also for this satellite ground truth data.
But again, what the satellites cannot do up to now is to go into the depths. Yeah. So the information that they got is from the surface or only for a certain depth. And we know that we often find so-called deep chlorophyll layers, which will not be seen by any satellite. And the spatial resolution is also a difficulty what we have. For example, this means that the satellite is very limited to get the information for a distinct position. It means that it covers a wider area, which may be an advantage for some reasons. But if you have localized high concentration, it will not be analyzed by the satellite itself.
This concludes our webinar today. We thank you for your time. If you have any further questions, please don't hesitate to reply to the reminder email I sent you, and I'll be sure to get your questions answered by Tobias and Detlev. So thank you again. I'll be sending out a link to this recording within the next few days, and we hope to see you again soon. Thank you.
Thank you very much.
Tobias and
Thank you
Detlev.
very much. Yes.
Thank you,
Thanks.
everyone.
Bye.
Thanks, guys. Thank you for attending this webinar. To learn more about the FluoroProbe, visit pbsystems.com.